Yes, so good evening friends, welcome once again to my channel and lecture number 29 of physics optional paper 2. Okay, and as promised by me, your syllabus will be over by January 2023. Okay, and as you already know that there are lot of comments which are there. This channel is already going viral. Okay, so more and more comments are coming, and I am thankful to those who are giving me the respect and love. Okay, but if you have any serious doubt, then you can surely contact me on 7249187038. Okay, my WhatsApp number. Okay, please do not make a call on this number. Already my incoming is stopped. I will recharge. Okay, so do not call on this number, but you can surely connect me with me on WhatsApp. Okay, and this is my Paytm number also. So if someone amongst you wants to give voluntary donations, then he or she may go for it. Voluntary donations I am ready to accept. Okay, so you can go for voluntary donations as well. Okay, if you want, that is voluntary. Okay, and someone was asking that regarding the state PCS, whether it is good or bad. I would say state PCS is not a bad option, but in my life I had got better opportunities. I cracked exams tougher than that. I cracked CSR net exam, which is, I think it is tougher than state PCS at least. So I cracked that. So that's why I did not give state PCS ever. But if you want to give state PCS, you can surely give it. It is not a bad option. I would say no exam is bad. Okay, and no work in this world is good or bad. Okay, no work in this world is good or bad. No exam in this world is good or bad. Only thing is you have to be you need to have faith in yourself, and you need to have the interest in that field. Okay, suppose if you qualify UPSC, suppose, but if you do not have the interest in administration, then there is no meaning of you getting qualified in UPSC. Okay, because what happens is, some people because of bhed chal means they keep on following certain people, so they qualify UPSC, and after going into service they are the most inefficient persons. Okay, so such things also happens in bureaucracy. Those who are not interested in administration sometimes qualify UPSC and become IAS, and then after they come in the service, they do not serve the nation at all. They just sit in the AC. Okay, so such people are also there. So it is basically a part of bureaucratic apathy. So why does that happen? That happened because the system in this country is such that if a person does BE, okay, if a person does BE, then everyone will try to do BE only. Okay, so that's why the engineering graduates are like a lump sum. Okay, the engineering graduates are so huge in number that you can't even imagine. Why it happened? Because people did not look at their interest. People just went on following certain other people. Whatever the majority of population is doing, I will do the same. Okay, so बहती गंगा में मतलब नदी के प्रवाह के साथ बहना बोलते हो जिसको, ठीक है ना, flowing with the river. Okay, it is called like that. So never be such a person. Never flow with the river. If you are interested in state PCS, if you find that UPSC is very difficult, then you should certainly go for state PCS. I am not against it. Okay, but the only thing is, whenever I see the question paper of state PCS, I really find it very kind of very low level. यार, means मजा नहीं आता उसके पेपर को देख के. Means if you look at the paper, then they will sometimes ask you that what is the photo behind ₹10 note. Now photo behind ₹10 note, a person should know or not in life. What does it even matter that a person knows each and every currency note in the circulation? Is it even important to is it even applicable to the service? After getting into service, is it even applicable that ₹10 note, what is written on the note, how many languages are there on the note? Is it even important after joining the service? Is it even is this knowledge even applicable after going into the service? The answer is clearly no. Okay, answer is clearly no. That's why I like UPSC, because they ask application based question instead of mugging up. Okay, so that's why I like UPSC. But if you are interested in state PCS, that's not at all a bad option. Okay, in my life I qualified exam better than that, so that's why I didn't give that. Okay, that's the thing. Okay, so I think we lost some 3 or 4 minutes in this discussion, but surely you should have learned this. So eigenvalue and eigenfunction, we will talk about this now. Now when we apply an operator on a wave function, okay, when we apply any operator on a wave function, then we get certain values. Okay, suppose if I applied an operator A on a wave function psi, as being shown here, I have applied the operator A on the wave function psi, then there are basically n quantum states. Okay, there are basically n quantum states, psi 1, psi 2, psi 3, so on and so forth up to psi n. There are n quantum states, and your operator when applied on psi will yield you normalization constant. Okay, not normalization constant, a complex quantity associated with that nth state, complex quantity an associated with it, with that nth state, means that observable, your observable an times your wave function psi n, which is the nth state of that wave function. Okay, so if I now someone would say that you had told us the general form, that operator applied on psi gives observable times psi. Okay, so that's a different story. That was a preliminary concept. Okay, that was preliminary concept. But now we are going to the advanced level. So at the advanced level, when you apply a hat operator on psi, you get an psi n. Okay, now an is your observable in nth state. Okay, nth quantum state, and psi n is your wave function of the nth state. Okay, psi n is your nth state wave function. Okay, wave function of nth state. Okay, so in Kate notation this can be written like this, that you might go for this for in the Kate notation. Only thing is you will substitute everywhere Kate. Okay, here it should be capital psi. Okay, I have written small psi, so change it to capital psi. So a hat Kate psi equal to an Kate psi n. Okay, here an is the eigenvalue corresponding to the eigenstate psi n. Okay, so corresponding to your eigenstate psi n, you have the eigenvalue an. Okay, and similarly, if we can also write it to be a n minus 1. Okay, psi n minus 1. Okay, so on and so forth it will be. Okay, but when a specific operator is applied, we will get a certain quantum state. It is not necessary that we will get the n state also and n minus 1 state also. It is possible that this might be invalid. Okay, this might be invalid, it is possible. Okay, but this will eventually become more clear in the forthcoming sessions. This is just an introductory part of what are eigenvalues. Okay, so we will read the definition once. Okay, we will read the definition once, that the only possible values that can be obtained from the measurement of an observable of a system whose operator is a hat are the eigenvalues an. The eigenvalue equation is written as like this, and in Kate notation it becomes like this. Okay, and here an is the eigenvalue corresponding to the eigenstate psi n. Okay, your an is eigenvalue corresponding to that psi n state. Okay, now the probability of obtaining one of the non-degenerate eigenvalues. Now what does it mean by non-degenerate eigenvalue? This you will learn in the upcoming classes. Okay, but for the time being, just accept it as it is, that for non-degenerate eigenvalues an, we have the probability formula, probability of obtaining non-degenerate eigenvalue an, we have the formula like this, something like this. Okay, so probability of obtaining non-degenerate eigenvalue an is given by this, and if the eigenvector psi is normalized, okay, if the eigenvector psi is normalized, then this term will be eventually 1. You have learnt in your preceding classes that bra and ket notation, what does that imply? This simply implies that integration minus infinity to infinity psi star psi d tau, okay, is equal to what? 1. Okay, this is the meaning of this, right? This implies eventually this integral, right? So its value will be 1 in case of normalized wave function. So if the eigenvector ket psi is normalized, then obviously you have this condition, and this denominator will become 1. So your probability of the particle being found in psi n state, okay, psi n quantum state, is simply this, okay, and an is your eigenvalue corresponding to that psi n state. Okay, now this is the formula Pn an is equal to this. Let this be equation B. Now we will solve one problem based on this. Okay, so let us consider a system in the state psi ket psi, which is given like this. This ket psi, for the time being, accept the things as it is. Okay, all these things will become eventually more and more clearer to you. These things will become eventually more and more clearer to you if you keep on attending the classes in succession. Okay, but if you get stuck over here, then I can't help with it. Okay, so you will have to keep patience also. So problem, consider a system in state ket psi, which is given like this. Okay, so where psi 1 and psi 2, ket psi 1 and ket psi 2 are the orthonormalized eigenvectors of the Hamiltonian of the energy. Okay, and eigenvalues are E1 and E2 corresponding to those. Okay, means energy eigenvalues are E1 and E2. What is the probability of finding of the system with energy E1? What is the probability of finding the system with energy E1? It is saying, right? So now let's see this. Now you know this very well, that we are seeing with respect to E1. So corresponding to eigenvalue E1, the wave function is psi 1. Okay, corresponding to eigenvalue E1, the wave function is psi 1. So this formula I told you. Now no need to go into the proof of this formula, because it is the postulate of quantum mechanics. This formula in itself is postulate of quantum mechanics. So no need to go into the proof of this formula. Okay, so this is the equation number 1 you are basically. Okay, now you know this very well, that I had told you one concept, that whenever this is there, okay, we will check whether it is normalized or not. Because the denominator we have to decide. So if it is normalized, then the denominator will be 1, but if it is not normalized, then the denominator will not be 1. Okay, so you know this very well, that this ket psi is given like this. So what will be your bra psi? Your bra psi will be basically 1 by root 2. Okay, 1 by root 2 bra psi 1, okay, plus bra psi 2, right? It will be like this. And when you will find this thing out of that, you will simply multiply these two, this multiplied by this. Okay, and after you multiply those two, what will you get? You will get an expression like this. Okay, an expression like this. And this expression consists of 2 more terms which are eventually 0. Okay, this term and this term. Okay, so these 2 terms are also there, but these 2 terms have become 0. So 0 has been written, and these 2 have become 1. Why they have become 1? Because it is given that they are orthonormal. So this is orthogonality condition, and this is normalization condition, because it is given that they are orthonormal. So they are both orthogonal, as well as normalized. Okay, psi 1 and psi 2. We had to find whether psi is also normalized or not. So we have successfully found out. Okay, and after we found out this, we got the bra psi ket psi expression equal to bracket psi equal to 1. Okay, bracket psi equal to 1. Now you know this very well, that this term, okay, it will be this only. Okay, and in the place of psi, now we have to find one more term, right? Why are we finding this? We are finding this thing because we have determined the denominator of this, but we have to determine the numerator also. Now to determine the numerator, you will basically take psi 1 psi. Okay, so psi 1 psi, after you take, okay, you basically take this bra psi 1, and in the place of this ket psi, you basically substitute the value which has been originally given to you in the question. Okay, originally given value to you. Then you substitute that value over here in the place of ket psi. So after you substitute that value here in the place of ket psi, you get an expression of this sort. Okay, an expression of this sort. And after you get that, you multiply this by this, and you multiply this by this. Okay, so basically this is normalization and this is orthogonality. So this will be 0 and this will be 1. In case you haven't revised the previous class concept, then you will find this class to be very, very difficult. Okay, suppose if in case you haven't revised anything of the previous classes, then you will find a lot of difficulty in following this class, because this class is totally based on your previous class concepts. Okay, so it has come out to be 1 by root 2. Okay, this value. Now you will substitute those values over here. 1 by root 2 square divided by 1. Why divided by 1? Because this is 1. You found out. So it will be 1 by 2. So your probability PE1. Okay, probability corresponding to what is this? Probability corresponding to what is this? Probability corresponding to energy eigenvalue E1. Okay, so this is the probability corresponding to energy eigenvalue E1, and it is equal to 0.5 as it has come out to be. And similarly you can find PE2 also. Now how will you find PE2? Whatever you have done in order to find PE1, you will just put 2 here, you will just put 2 here. Okay, then you will basically have 2 here. Okay, so after you have 2 over here, then you will have 2 over here, right? You will have 2 over here, you will have 2 over here. Okay, and so this term will in fact become 0, because it is orthogonality condition and this is normalization condition, so it will become 1. So again you will get 1 by root 2 only. So similarly you can find out the probability corresponding to eigenvalue E2 also. So this is the probability corresponding to eigenvalue E2. Okay, so in this way your problems can be solved even if you don't know the in-depth concept. Okay, now right now you didn't know any in-depth concept, still you were able to solve this problem. Okay, so in this way your problems can be solved very easily. Now we will move on in the next class towards our next topic. Till then,